and therefore the stability enhances. So the cycle, the most of the times these Shabina, मैंने 10 बार बोला दरवाजा बंद कर, तुम्हें सुनाई नहीं दे रहा है? तो so most these ये वाला दरवाजा यार शोर आ रहा है वहां से. Most of the time these chelating rings are organic compounds, and by virtue of this property, because bulk of the structure then becomes organic, only one of the corners of the ring, and because of this the dominant part of the structure is organic. The chelate complexes are most of the times soluble in the organic solvents, and they are insoluble in water. So it becomes an opportunity. It provides an opportunity for for making a complex soluble in organic solvents, and you can be separated from other constituents by a process which we call solvent extraction. So we are extracting a metal in the organic layer by forming a chelate complex. Right. So chelate is chelate effect enhances the stability of the complex. And if the ring, if the organic molecule is already branched, it is sort of uh, cyclic in structure, the chances of the ring formation are greater, rather than if the ring is, if this the original chelating ligand is straight chain compound, then it has to fold, the ring has the ligand has to fold itself around a metal ion, and the process becomes little bit of slow. And therefore the geometry and structure of the ligand is important. And if the structure is already without metal ion, if the structure of the ligand is such that it is already cyclic, which we call macrocyclic ligands, then of course the effect becomes more pronounced than the simple chelate ligands. So enhanced affinity of the chelate ligands for a metal ion compared to the affinity of a collection of similar non-chelating monodentate ligands for the same metal. Say, for example, you have an amine ligand, normal monodentate amine, ammonia or its substituted ammonia, that is primary amine or secondary amine, and then you primary amine primarily, and then you have ethylene diamine, and you compare the stability of the same complex of the metal with same metal ion, same oxidation state, same coordination number with ethylene diamine and ammonia, you find out that complex with the ethylene diamine is pretty much more stable than the simple monodentate ligand. So that is the impact of the chelate effect. So this results in larger values of the overall formation of the formation constant for chelate complexes than the monodentate complex. So example that I gave is ethylene diamine and the glycinato complexes. These one is known as symmetrical chelating agent, other is known as unsymmetrical chelating agent. So characteristic features of the ligands are that the chelating ligands are, obviously they need to be polydentate, they need to have more than one donor atoms in their structures, which can simultaneously bind themselves with the metal ion. So you can have a bidentate ligand, tridentate ligand, and hexadentate ligand. And the a bidentate example is ethylene diamine or acetyl acetone, or for that matter oxalate, or there are a host of ligands which act as glycine. They're all bidentate ligands. Then this is tridentate ligand, and then propane, 1,2,3 triaminopropane, and uh, this is the tridentate ligand, and two molecules of this compound will satisfy the 6 coordination number of the cobalt. Then you have triethylene tetramine, which has 4 amine groups, 1, 2, 3, and 4, and it can form 3 rings around the nickel atom. So for 4 coordination number is satisfied by this one molecule. Then you have tetraethylene pentamine, which is written as tetraene. This is triene, and it has five amino groups, and therefore its coordination it is pentadentate. Five donor sites are there. This is the complex formed by this ligand. Then ultimately we introduce this compound which is known as EDTA. We will will design you have a practical also to find out hardness of the water, temporary and permanent hardness of water, and for that we use complexometric titration. We hardness of the water is because of the calcium and magnesium salts, chlorides and sulfates of calcium and magnesium, and these two metal ions determine the hardness of a water, and they are estimated, their concentration is determined by a titration which is called complexometric titration, in which calcium and magnesium ions are complexed by this very ligand EDTA. It is tetrabasic acid. There are four carboxylic acids, and we all know that carboxylic acids are acidic, but they are weakly acidic. So the salt that is marketed is disodium salt. Only if the first ionization energy is quite good, second one is not that efficient. You cannot take away hydrogen atom from the second OH group as easily, COH group as easily. So this compound is marketed as disodium salt of the ethylene diamine tetraacetic acid. Then when you use it in the solution as complexing agent, you have to remove these all hydrogen atoms from the carboxylic group. That can be done by using a strong base or by providing the pH above 10. That is the primary condition for using this reagent as a complexometric agent. So it will complex as calcium ion. One calcium ion will react with one molecule of EDTA. We will talk about this process, this estimation, this reaction, and the calculations which are involved in the practical class. So that is EDTA complexometric titration. So it has two amino groups, two nitrogen atoms, which amino groups, which are then substituted by acetate group, and four O negative groups, and therefore it's hexadentate. And this is the ring structure, the how it occupies the six coordination sites of an octahedron, distorted octahedron complex. Now let's go to the stability. The chelate agents bind with the metal centers of suitable site firmly, and bond can be covalent or coordinate. This depends upon the nature of the donor site. So if you talk about the ethylene diamine or these amine groups, the bond is 100% coordinate, in the sense that nitrogen is already trivalent, and it is having each of the nitrogen atom is trivalent already, forming three regular covalent bonds, and then nitrogen, each of the nitrogen atom has a lone pair of electron, and that lone pair is used to form a fourth bond with the metal atom. And certainly this fourth bond is not a covalent bond, it is coordinate bond, because nitrogen is using its lone pair of electron to donate that into the vacant orbital of the metal and form the fourth bond, the coordinate bond. But if you come to the ethylene diamine, this nitrogen is forming again. Here it is trivalent. It has lone pair. That lone pair will be used to form a bond with the metal. So it will be a coordinate bond. Same is true with the nitrogen atom. So two nitrogen atoms are forming coordinate bond. However, this oxygen atom is monovalent here. It is having a negative charge, and the oxygen atom was forming, its oxygen is always divalent. It forms two regular covalent bonds, which can be polar or polar covalent bonds or pure covalent bonds, depending upon the substituent which is there. It was having an OH here, so that H has been lost as H positive, so it can form a covalent coordinate bond with the metal. That's the difference between nitrogen and oxygen. That oxygen is deficient here valency wise, so it has to form a second bond. So the bond with the oxygen is not pure coordinate bond, it is covalent coordinate bond. So the extent of coordinate bond is limited in the case of oxygen. However, in the case of nitrogen, it is full coordinate bond. This makes chelates more stable than their non-chelate counterparts. So this is the hexamine iron 3 plus. This is phenanthroline. Phenanthroline is, yes. Phenanthroline is an cyclic compound in which two pyridine ring. This is one pyridine ring. This is second pyridine. They are joined together through a bond, and then benzene ring is fused here. Or you can say this benzene ring is fused with this pyridine ring, and it's also fused with this pyridine ring. So you have one, two, three, four. Four and fifth member is metal. So five-membered ring formed by the two nitrogen atoms, two carbon atoms, and one metal atom. So phenanthroline, because of this extensive pi bonding, there are one, two, three, four, five, six, and seven. There are seven pi bonds in conjugation with each other. So there is extensive conjugation, delocalization of the pi electron, and therefore the pi star orbitals have much lower energy, and they are best. The phenanthroline is a best pi acceptor, and by virtue of being best pi acceptor, it is a strong field ligand. It can form low spin complexes with any metal ion. So phenanthroline is a chelating ligand. It forms a five-membered ring around the metal ion. So five and six-membered chelate complexes are more stable than three and four. Why? Because three and four membered rings are in steric strain. The bond angles are less than 90 degrees, and that is pretty much difficult for for carbon atom or for the nitrogen, the metal atom, to form a stable ring. And the chelating agent without multiple bonds like ethylene diamine prefer five-membered rings, while the chelating agent with multiple bonds which are conjugate in each other prefer six-membered ring. So five and six-membered rings are more prevalent, more dominant, and in case of neutral ligands, the five-membered rings are dominant. In case of there is resonance in the ring, so six-membered rings are more stable then. So this is four-membered ring: cadmium, ethylene, two amino groups, dimethyl, uh, amino methane. So the ring size is 4. So log K is very small. When you have the ethylene diamine, then the ring size becomes 5. The log K becomes 5.7. When you have six-membered ring, the uh, the stability of the complex decreases. It is 4.7. And when you have seven-membered ring, it is 3.6. So for neutral ligands, neutral chelates, five-membered rings are much stable than six-membered or seven-membered, or the three-member or four-member. So chelating agents with bulky groups form less stable complexes. If there is bulky group substitution on the donor atom or adjacent to the donor atom in the ligand, then the complex becomes less stable because of the steric hindrance. And the example is bipyridine. But this is a simple bipyridine, two pyridine rings linked through carbon-carbon bond. This is complex with tris complex with the iron 2, forming a distorted octahedron complex. This is more stable than two pyridine, bipyridine again, 4,4 bipyridine, and then linked with the methyl groups 4,4 dimethyl 2,2 bipyridine. So at four positions and 4' position, you have two methyl groups adjacent to the donor atoms. So because of this steric hindrance, the compound is less stable. So then what is the thermodynamic origin of the chelation? We all know that the free energy change is given by delta H. Free energy change is enthalpy of the standard enthalpy change minus TdS temperature into standard entropy change. Also, the free energy change is linked with the equilibrium constant, because equilibrium constant is a thermodynamic parameter, and free energy is also a thermodynamic parameter, and two are related like this. So if the k has large value, delta g becomes negative, because this is minus RT large negative. And when you have delta G large negative, then we say that the equilibrium constant has large value, free energy change is more negative, and process is spontaneous. So any complex which has which is more stable will have the large positive value of the equilibrium constant, and thereby having large negative delta G value. So how can you make delta G value more negative? If you have delta H negative and delta S positive, that is the standard requirement for delta G to be negative. You need to have enthalpy change negative and entropy change positive, or the reaction should be exothermic, and the entropy wise there should be more randomness during the formation of that complex. So if there is less randomness, entropy decreases and process becomes non-spontaneous. And if there is endothermic reaction, it is non-spontaneous, heading towards non-spontaneous. If it is exothermic, it is spontaneous. So difference in delta H between chelate and non-chelate. If you compare the standard enthalpy change during the formation of an chelate complex and the corresponding non-chelate complex having same donor atoms, then there is little difference, because the metal ligand bond is as strong as almost as strong in the in the polydentate ligand as in the monodentate ligand. The only difference is the chances of the occupation of these coordination sites in the case of polydentate ligand is high, and the rate of formation becomes high, and therefore the extra stability is derived, because the ring structure gives the extra stability. So non-chelate is almost next, because similar metal donor types are present in both cases. Therefore, delta G difference primarily arises from the entropy change. There is little difference in the enthalpy change in the case of chelate and non-chelate. So fundamentally, if the delta G is different for chelate and non-chelate, stability difference is there. We all know that chelates are more stable than non-chelates. Then it must be arising from the entropy change. So delta G is difference primarily, the difference arises from primarily from the entropy change. So when delta G is more negative, uh, we say for chelates it is more negative, and for non-chelates it is less negative. So entropy change positive, and there must be more positive entropy change for chelates, and that will make the equilibrium constant more numerically having higher value than the non-chelate complexes. So stability of the complex increases therefore with the increase in chelation. So here is an example: cadmium tetraaqua complex plus 4-methylamine, giving four methylamine groups coordinate with the cadmium. Four water molecules are released. So this is one molecule as a whole, and these are four molecules. So number of molecules in the reactant are 5, and here one complex molecule plus 4 water molecule 5. So there is no change in the randomness. There are 5 molecules in the reactant side, 5 molecules on the product side. Look at the situation when you have an ethylene diamine ligand as an substituent for the water molecules. So you have one complex molecule and two ethylene diamine molecules. So you have three molecules in the reactant side, and one complex molecule and four water molecules getting replaced. So 4 plus 1 is 5. So there is large increase in the randomness. You have three molecules on the reactant side, there are 5 molecules on the product side. So this type of situation where you have the randomness increasing in the chelating ligand, so this increases the entropy change, which in turn makes delta G more negative, and delta G more negative makes thermodynamic constant more positive, and when it makes thermodynamic constant, equilibrium constant or stability constant more positive, it means that complex is more stable than in the chelate complexes than in the non-chelate ligand. So chelation is thermodynamically favorable. So the origin of this extra stability of the chelate complexes is entropy, change in entropy. There is more randomness during the formation of chelate complex than the randomness that is found in the non-chelate complexes. Similarly, if you have triene, which has four coordinating sites in one molecule, so you have one molecule of triene and one molecule of complex cadmium tetraaqua complex. So two molecules on the reactant side and one molecule of triene and four water molecules, five molecules on the product side. So the randomness here increases more, and therefore cadmium triene complex should be more stable than cadmium bisethylene diamine complex, which in turn is more stable than cadmium methylamine complex. So cadmium triene more stable than cadmium ethylene. So because delta S is more positive in the case of cadmium triene complex. So therefore, stability of the chelate complexes increases with the denticity of the chelating agent. We saw that the triene is tetradentate and the ethylene diamine is bidentate. So as the denticity increases, the chelation increases, and therefore stability increases because randomness increases in the tetraene as compared to ethylene diamine. So Nazia, पानी पिलाना पानी factors affecting the stability of chelate complex. What are the factors which influence the stability of chelate complexes? So first one is size of the chelate ring. As I said earlier, 5 and 6 membered rings are more stable than the lower members are higher members, 7 or 8 membered rings or 4 membered rings chelating due to the strain, less steric strain. Nazia, phone lana mera. So this is carboxylate. Nazia. So this is log K for carboxylate. This is formic acid, uh, and this is oxalic acid, and then uh, ethane dioic acid, then propane dioic, butane dioic acid. So these so as you see that the size of the ring increases as we go. Hello. So as the size of ring increases from 4 member to 5 member, so equilibrium stability constant increases, and then when it goes down to 6 member and 7 member, it diminishes. So size of the ring has optimum value for the stability constant is 5 and 6 member ring, depending upon on the situation. If there is no there is no conjugation inside the ring, then 5 member ring is more stable. If there is, in this case, there is no conjugation inside the ring. If there is conjugation inside the ring, then 6 member ring becomes more stable. So number of chelate rings and nature of metal ion. As the number of donor atoms increases, the stability of the metal chelates also increases. We saw it earlier. Stability of the chelate complex is also uh, lie in line with the Irving Williams series. So this is the tetraamine complex, then ethylene diamine bis, then triene, then uh, uh, diene 2 times, and then pentaene, 5 coordination number. So there is no chelation here. There is the bidentate, this is tridentate, this is tetradentate, and this is pentadentate. So these are equilibrium stability constant, overall stability constant for different metal ions. You can see For even monodentate ligands, the equilibrium constant increases all the way from iron, cobalt, nickel, and it has maximum value for copper and then diminishes. We saw it earlier also. And uh, for cadmium, if you go in a group zinc to cadmium, because zinc has smaller size than the cadmium, zinc, cadmium, and mercury are in the same group. So cadmium has lower stability constant. Cadmium complex has more lesser stability constant than the zinc complex because zinc has the smaller size, right? And look at the ethylene diamine base complex. It The trend is same. Now the manganese has higher coordinate. From manganese it goes to iron, size goes on decreasing along the period, and stability constant increases. Again, the peak value is for the copper, and then zinc has smaller value and cadmium has still smaller value. So same goes here for the triene and same for pentaene. Everywhere the trend is same, copper has the peak value. So in addition to the prediction by the Irving Williams series, Melee and Meller series. They have also studied series of complexes, uh, and they determined the stability constants of various complexes. And this is the series. This is the order that they have predicted, that complexes, palladium complexes, are more stable than copper, then nickel, then cobalt, then zinc, then cadmium, then iron and magnesium and magnesium. Obviously, again following the more or less the size. So in addition to prediction by this is the same thing, stability of the chelate complexes. Now, third thing is resonance effect. Resonance stabilization of chelate rings. As I said earlier, there are certain ligands which have multiple bonds in conjugation. This is beta di. This is a class which is known as beta diketones. So acetyl acetone, we have one double bond, carbon oxygen double bond in conjugation with carbon carbon double bond. So negative charge is delocalized from this oxygen to this oxygen. Next, in the next canonical structure, this negative charge can come down and form pi bond here. This pi bond will move from here to here, and this pi bond will move to the oxygen and negative charge. So this is the other canonical structure. So because negative charge is delocalized from one oxygen to the another, we represent this cyclic compound, ring compound, by an arc inside the ring and negative charge inside that ring. So indicating that a negative charge is delocalized from one oxygen to the other. And this is obviously a six-membered ring, two members by oxygen, then three carbon atoms, and one iron atom. So six-membered ring and flat ring, hexagonal ring, and just like benzene, because there is aroma, there is resonance, and resonance demands that all the atoms which are involved in the resonance should lie in one plane. So Lewis base strength and charge of the ligand. So Kelvin and Wilson studied a series of copper chelate complexes, and they found that stability of the chelate complexes increases with increase in the basic character of the ligand. So this we already in the outset also I said that in the complexes with 3D metal ions with water, halides, and water, fluoride, and ammonia, the basic character of ammonia is highest, and the complex formed with ammonia is more stable than water, and water complex is more stable than complex formed with fluoride, because the basic strength decreases in that order. Ammonia is more basic than water, and water is more basic than fluoride. So uh, the uncharged, the stability of the complex increases with increase in the basic character of the ligand. Moreover, the uncharged ligands like ethylene diamine and triene form more stable complexes than anionic ligands like oxalate and glycinate. This is also an example that basicity plays its own role. So ethylene diamine complex with nickel diaqua, this ethylene diamine complex log beta is 14.4, and if you have the glycinato complex, which is negatively charged ligand, one end is oxygen negative and other is amine, the log beta is 14.4. So same metal ion, same coordination, same set of ligands, with the difference that one side you have ethylene diamine, and on the other side you have glycinato complex. So glycinato complex is less stable than ethylene diamine complex. So next is steric hindrance and strain due to large ligands. So chelating ligands with large groups, they become bulky. They avoid provide hindrance to the approach of the metal ion, and the bond formation becomes difficult, and therefore steric hindrance always decreases the stability of the complex. Uh, and this weakens ultimately the met strength of the metal ligand bond due to steric hindrance. So ethylene diamine forms more stable complexes with divalent metal ions than N nitrogen tetramethyl. So if you have substitution at the donor side, that is particularly damaging. So if you have hydrogen atoms here at the NH2, if you replace these two hydrogen atoms by two methyl groups, so it becomes NN tetramethyl ethylene diamine. The complex will be very less stable. It will lose overall stability, will be affected by the strain in the chelate due to the particular geometry of the chelating ligand. For example, triene complex of copper is more stable than tren complex due to less steric strengths of the triene, as triene can adopt square pyramidal geometry. The ligands that we earlier discussed, these ligands. Come here. Yes. Hmm. Yes. Uh, this is this is one ligand. Uh, this is straight chain ligand. This is known as triene, and this is the other ligand which is like this. This is three coordination. This ligand can easily adopt the square planar geometry, and this cannot adopt the square planar geometry. So there is strain. So particular geometry of the ligand also provide favors. If the geometry is easily adopted, square planar geometry is easily adopted, then the chelate becomes more stable. Uh, this is the example. So this is ethylene diamine, and upside also there is one ring. So this is that triene complex. Log beta is 20.5, and there is less strain. And the other is this ring compound. One CH2, CH2, and N. You have ammonia molecule. Ammonia molecule में तीन हाइड्रोजन एटम है. तीनों के तीनों को सब्स्टिट्यूट कर लीजिए इथिलीन डायमीन से, CH2 और NH2 से. This is CH2, this is CH2, and then NH2. This is nitrogen somewhere here. इसमें तीन ग्रुप जुड़े हुए, एक CH2 CH2 NH2, एक CH2 CH2 NH2. So this is एक तो तीन नाइट्रोजन एटम, तीन NH2 ग्रुप्स हैं, और चौथा हो गया नाइट्रोजन खुद. So this is also tetradentate. ये वाला भी tetradentate है, but this forms more stable complex because metal can easily adopt the square planar geometry here. It cannot adopt square planar geometry because there is strain in the ring. So this is less stable. Log beta is 18.8. The stability constant is higher there. So this is tren. Tren is एक अमोनिया मॉलिक्यूल है. अमोनिया में तीन हाइड्रोजन एटम है, एक NH CH2 NH2, इधर से भी CH2 NH2, इधर से भी CH2. This is this ligand, and this one ligand is कि NH2 CH2 है, फिर NH, फिर बीच में ब्रिज दोबारा CH2 का है, और then you have NH and CH2. This is known as इथिलीन डायमीन. इसमें तीन है, एक ऊपर है, एक ट्राई इथिलीन डायमीन टेट्राएमीन. So what are then what are the ultimate applications of these chelate complexes? Number one, we will study this effect in removing the hardness of the, not only removing, but the determining the extent to which the water is hard. That is the removal of hardness by making soluble. You add some chelate agents which form complex with the calcium and magnesium, and then make that complex should be water soluble. तो आपका फ्री कैल्शियम और मैग्नीशियम नहीं होगा वाटर में, विच वुड अदरवाइज इंटरफियर विद द फ्रॉथ फॉर्मेशन, जो सोप के साथ एक कॉम्प्लेक्स बनाता है और फिर वो झाग नहीं बनने देता था, आपकी कपड़ों से मेल नहीं निकलती है, मतलब डिटर्जेंट इफेक्ट को नलीफाई कर रहा था। वो कैल्शियम और मैग्नीशियम आपके बाउंड हो गए किसी कीलेटिंग लिगेंड के साथ, और फिर वाटर सॉल्युबल, पानी में ही सॉल्युबल फॉर्म में रहे, but then calcium and magnesium are not free. So this is an um, the use of the chelatic effect for our advantage, that we remove the hardness of the water by adding a suitable chelating agent which forms chelate with the calcium and magnesium, and then that chelate complex is soluble in water. So calcium and magnesium remain in water, but they are not free to form a complex with the soap. They are bound with the chelating agent, right? Similarly, you can form chelate with the metals, and that chelate with the metal is soluble in organic solvent, and therefore you can purify metal, you can separate metal from other things. So chelates are also used as food preservative. So food preservative, they you know they you know form the chelates with the metal, so make metals unavailable for for decaying the food. So because of this chelation, the metals which were responsible for decaying, or change of the food, or the removing the water, moisture, or any other things from the food, so that it was decaying quite easily, quite early, because of the making the metal ions unavailable for the process. The chelates are formed, and therefore the life of the food, shelf life of the food increases, and that's the chelates are act as the food preservative. So EDTA eliminates harmful radioactive metal ions. Many EDTA forms complexes with many radioactive metal ions inside the body, and forming them water soluble chelates. Therefore the harmful impact of the metals is nullified. And lastly, the many chelates are colored complexes. They form many chelating ligands form colored complexes with aluminum, which is otherwise colorless, nickel, magnesium, and because of the color formation, they can be used. These chelates complexes can be used for detection and estimation of these metal ions. Will specifically study how the hardness of the metal is not only removed but estimated by this chelate effect, when we discuss in the next practical class the application of the EDTA as a complexometric agent to determine the hardness of a water sample. So that finishes today's lecture. We will go now next time to the discussion on how the stability constant of complexes can be estimated, determined by particularly by two techniques that are mentioned in your syllabus: spectrophotometric and pH metric techniques. So spectrophotometer, if you have read, is an spectrophotometer instruments are used to determine the absorbance, or one is the absorbance, other is transmittance of a solution. And what is absorbance and transmittance? Absorbance is log I0 by I is called absorbance, and transmittance is log I by I0. So reciprocal of the absorbance is transmittance, and transmittance reciprocal is absorbance. And this is based on a law which we know call it Lambert-Beer law. So which says that the absorbance log I0 by I is equal to is directly proportional to the concentration, and it is also directly proportional to the path length, and it is the proportionality constant is nature of the solute. So there is when photon beam is passed through a solution, the absorbing there is then it passes through the solution, and then it goes into the detector. the detector compares the intensity that was incident on the solution, uh, and then which has transmitted from the solution. So it compares the intensity of the two beams, the incident beam. In fact, what is done, that the when you have an lamp which is UV lamp or the visible lamp, it generates, it is put on by the with the help of the electricity, it generates radiation in the visible region or the UV region. Then we select a wavelength which passes through the filters, and then there is a system called beam splitter inside the instrument which splits beam into two parts. एक beam को दो parts में डिवाइड करता है. वन पार्ट ऑफ द बीम पासिस थ्रू द सॉल्यूशन, जिसका आपने सॉल्यूशन बनाया और वो उसके पाथ में रखा हुआ है. अदर passes through the pure solvent. So then there is detector on the other side which receives both beams, one which has passed through the solution, which is your test solution, and other which has not passed through the solution or pure solvent. And then it compares, detector compares the intensity of the two beams, and it has the knowledge that how many photons were originally coming inside the beam when the beam was passing, when beam was incident on the solution. So I0 is the intensity of the incident beam, and I is the intensity of the transmitted beam. So it compares the two beams, one which has passed through the solution, one that has not passed through the solution. So the decrease in the intensity of the transmitted beam is directly proportional to the concentration of the absorbing material. So there are solute particles in the solution which are absorbing the radiation and going to the excited state, because this is the radiation which must have the same energy as the energy difference between ground state and the excited state. And the number of photons that get decreased in the transmitted radiation is equal to the number of molecules present in the solution which are absorbing the radiation, because one molecule absorbs one photon. So that correlation is developed. We will talk about this in the next lecture, how this instrument is then used. We will, if there is time for the offline classes, we'll do an experiment also on this, how you can find the composition of a complex and stability constant of a complex by spectrophotometric method experimentally. We'll do an experiment also on that if the situation allows that. So thank you for today's class. If you have any questions, I am here. You can ask me if you have any questions. If there are no questions, I'm going to log out because I have to go. It's
Okay,
okay.
sir.
Thank you.
Thank you,
Thank you.
sir.
Thank
Thank
you.
you, sir.
Thank you.
Thank you.